Good morning, everyone. My name is P. Mohit from CACD section, and this mathematics for computing complex engineering problem brought you my topic of Hamiltonian cycles in robotics navigation. Their optimization robot paths through cyclic loops. Now, in this, we'll see Hamiltonian cycles, introduction to them, algorithms for finding Hamiltonian cycles, will be implementation in robot navigation, and challenges in future directions. Now, coming to the first introduction to Hamiltonian cycle, we see that we have to understand this topic, definition of basic concepts, importances in graph theory, and differences between Hamiltonian and Eulerian cycles. Eulerian cycles and Hamiltonian cycles are totally different, and I'll explain why. First is definition and basic concepts. We see the Hamiltonian cycle visits each node or each graph vertex exactly once, returning to the start, crucial for path optimization. Next is importance in graph theory is to ensure complete graph traversal, critical for optimization, robotic navigation, and route planning algorithms. Now, the difference between this and Hamiltonian cycles are Hamiltonian cycles visits each vertex exactly once, while Eulerian cycles traverse each every edge once. Difference lies in the traversal criteria. So in Hamiltonian's exactly once in vertices and in Eulerian in exactly adjacent once. Okay. Next, in relevance to the robotics navigation, we have application in path planning, where Hamiltonian cycles optimize robotic path planned by ensuring efficient collision-free coverage of all target points. We have challenges in robotic environments where dynamic obstacles, sensor noise, and complex terrains increase the difficulty of finding Hamiltonian cycles in robotic navigation, where this might be a problem. In real-world examples in robotics, robotic vacuum cleaners use Hamiltonian cycles to efficiently cover every area without repetition. So it goes from point from our carpet to our sofa in exactly once. It won't visit back again because it's already cleaned. That's the simple logic of Hamiltonian cycle. Now, algorithms for finding these Hamiltonian cycles are backtracking method and dynamic processing approaches. So, backtracking method explores all vertex permutations, pruning invalid paths to find Hamiltonian cycles efficiently. For dynamic programming approaches, it solves Hamiltonian cycles by storing sub-problem solutions, reducing redundant computations efficiently. In complexity issues, we see that each algorithm of Hamiltonian cycles have exponential time complexity, limiting practical use in large graphs. In heuristic and approximation methods, we see that we have genetic algorithms and colony optimization and benefits and limitations. Let's go on. The first one is genetic algorithms. Genetic algorithms iteratively evolve solutions using selection, crossover, and mutation to approximate Hamiltonian cycles effectively. In ant colony optimization, it uses frenome-based heuristic to probabilistically construct near optimal Hamiltonian cycles. In the benefits we can see are faster solutions, but may miss optimal cycles. Approximation balance speed with solution quality, yet lacks the guarantee. Now, in implementation in robotics navigation systems, first is the mapping the environment as a graph. So, environment mapping converts physical space into graph models and representing these graph nodes and edges, representing feasible robot paths. Second is using Hamiltonian cycle for coverage path planning. So, Hamiltonian cycles ensure complete, non-repetitive coverage in robot path planning, optimizing navigation efficiency. Third, we must use the multi-robot coordination where Hamiltonian cycles enable the efficient multi-robot coordination by ensuring collision-free, complete area coverage, and through optimized path synchronization. Next, let's see some case studies and simulations where we have already discussed the autonomous vacuum cleaner application. Now, optimal path planning via Hamiltonian cycles ensures complete, non-redundant area coverage in autonomous vacuum cleaners. We see warehouse robot route optimization. We use Hamiltonian cycles to reduce travel time, improve efficiency, and minimize collision risk. Simulation tools and results such as ROS and Glazo validate Hamilton cycle efficiency in robot planning and optimal coverage. Let's see some challenges and future directions where computation complexity in large environments, um, where current approach struggles with real-time adaptation to dynamic and unpredictable obstacles in navigation environments. In emerging trends, we see machine learning integration, real-time adaptive algorithms, and potential for autonomous system expansion. Coming to the first thing is the machine learning integration, where machine learning or ML enhances real-time path prediction but requires extensive training data and computational resources. Without them, we can't actually access those machine learning algorithms into them using Hamiltonian cycles. Next, we have real-time adaptive algorithms, where it optimizes path finding by dynamically adjusting to environmental changes and sensor inputs. Right. Next, for potential for autonomous system expansion, where Hamiltonian cycles algorithms enables autonomous systems to navigate increasingly complex environments efficiently. Thank you. Now we'll be looking on some Python code, how to find these Hamiltonian cycles using for robot navigation. Um, yeah. Now coming to this piece of code, as I say code snippet, we see here is the Hamiltonian cycle in robotics navigation using backtracking method. Now we open a Python code. This is a Python code where we have a related output as well. Now we open a function isSafe for a vertices, graph, path, and position. Now we have to check if vertex v or vertices v can be added in the required index position in the Hamiltonian path. Now we have to check if this vertex is connected to the previous one. So using an if loop for a graph of path of position minus 1 of v equal to 0, we have to return false. Else, if it is already included, return false. If not, then you have to return true and independent. Now, we'll be using Hamiltonian cycle. This is the main code or main logic of Hamiltonian cycle. The formula finding the number of Hamiltonian cycles is n into n minus 1 of flow divided by 2. Now, for recursive utility function to find the Hamiltonian cycles. But why are we using here recursive method? We could use normal for loop and just do it off, right? Well, the reason we are using recursive method is to repeatedly check until it forms a cycle. So base case, if all vertices are included, if position equal to length of graph, then you have to check if the last vertex corrects the first one or the starting vertex. So you have to return the graph of position minus 1 and path of 0 is 1. Then you have to try different vertices as next candidates. We'll be using a for loop for v in range of from 1 to the length of graph. If isSafe of graph v, we have opened the first code. If this comes in this state, now path of position will be our vertex. If Hamiltonian cycle util of this is okay, now we're using this method where the recursive utility function will be using in the if Hamiltonian cycle util method, we have to return it true, and using the backtrack of position of path of position will be our minus 1. So it keeps on going to the previous one and checks out. Then we have to return false. Now after writing this, it gives a normal 0, 1, 2, 3, and again it backtracks to 0. So wherever you check, it visits each vertex exactly once. Okay. So 0, 1, 2, 3, 0. Now this 0 is actually connected here, but the program has repeated 2 times. So don't think that it has visited twice. Is it coming back to 0? It has pointed back to 0. So this is the basic Python code for running the Hamilton cycles in robot navigation using the backtracking method. Thank you.